That's loud. Yeah, okay. I'll slow down here. So, good news, bad news, and it all has to do with there's nobody following me on this, so I can talk for as long as I want, which might help to answer some of your questions, but anyway, I could go on for a long time. What I want to talk about today is RISC-V models for verification, software development, and architecture exploration. So let's jump into this and actually just start with RISC-V. And with RISC-V, it's the freedom and not the free. This is why RISC-V usage is growing so fast. And so that's one of the things we want to talk about today. How do RISC-V models accommodate this freedom, and how does that accommodation in the models flow into the use cases of verification, software simulation, architecture exploration? So high quality RISC-V models are required for RISC-V success. Simon touched on this in his keynote this morning, but for the use cases that we're seeing here, architecture analysis, including especially custom instructions for software development, debug and test for processor and SoC, verification, you need high quality RISC-V models. Anyone can build an instruction set simulator. Most of us have done this in our college days. Anyone can build an instruction set simulator. It's viewed as a commodity item, but more than just an ISS is actually needed here. So just to give a bit of background on Imperas and Imperas and RISC-V, the Imperas founding team has a background in design automation tools and also FPGA and processor IP companies. We started in 2007 looking at software simulation and trying to carry some of the lessons that we had learned in our previous lives over to embedded software development. And so this required, this software simulation use case required us to build high quality models of embedded processors like ARM, like MIPS, like Renesas. Actually, we currently support something like 15 different ISAs. So we've done well there. We self-funded the company, we built a business in this area. In 2016, we realized that the RISC-V community would need RISC-V models for software development. And there was and still is actually a very large demand for RISC-V models for software development. But there's also a need of models of custom RISC-V cores and a need for verification of those cores. And so Imperas started working actually first on compliance and then on processor verification with RISC-V International, with the Open Hardware Group, and with customers such as NVIDIA Networking, NSI Techs, MIPS, Codasip, Silicon Labs, and more. So we developed the RISC-V OVP Sim Plus ISS. This is freely available on our Open Virtual Platforms website, and this supports the complete RISC-V specification that is ratified. It also supports the stable unratified pieces of this specification. And between our commercial customers and the users with a free RISC-V OVP Sim Plus, Imperas RISC-V processor models are used in almost every RISC-V project. And just to show this a little bit more, we've got NVIDIA Networking, NXP, Silicon Labs, Seagate, Nagravision, just down the list there, quite a number. But one of the key things is the free RISC-V OVP Sim Plus and more than 100 different organizations using the free. We also have processor IP partners, certainly working with RISC-V International, which is not producing processor IP, but definitely a collaborator. And then down the list of these different processor IP vendors. And then also working with different tool partners to make sure that the ecosystem around RISC-V is actually a vibrant ecosystem that can support these different use cases. So what are we looking at here in terms of the use cases? What are we looking at here in terms of the tools to support that? So we have the RISC-V reference model. The RISC-V reference model, again, supports the full specification. We have in the light blue here, we have the ability to configure this base model. So more than 250 different parameters. So again, that's going to cover everything in the specification, everything even not ratified but stable in the specification. And then the orange box there is where custom instructions go. So the nice thing is that every one of our users using RISC-V OVP Sim Plus, using our commercial tools, is actually using the base model. So that base model gets used every day by at least tens of users, if not all 100 users. So that gets used a lot, and any custom instructions and CSRs get put into that extension library. So now what happens? Now we get to go and use this reference model in a design verification flow. This is the design verification flow with Imperas. We've got the RISC-V reference model here, and then verification IP in the lighter blocks. And then also here we've got the RVVI RISC-V verification interface standard that is enabling communication between the test bench and the reference model subsystem there. We've also got the Imperas debugger there, and that works well to enable hardware-software code debug in the DV environment. So that's one use case. That's DV flow there, and then the second is the virtual platform or software simulation environment, and there again we've got the same reference model. Apologies, showed it in a different color there. We can actually model the full SoC, including behavioral and peripheral models. And then we have the simulator engine and the tools, the same debugger here. And then the VAP tools are verification, analysis, and profiling tools. These are software tools, trace, code coverage, profiling, memory monitoring, and more. That are part of the simulation environment. So we've talked in general about this, but let's talk a little bit more about the requirements for the RISC-V model. So of course it needs to model the full ISA, all versions of the ratified spec, the stable unratified versions. Needs to be able to model other behavioral components like interrupt controllers. Imperas supports Click, Plick, Clint, AIA. I think those are the 4 different interrupt controller versions. You need to easily be able to update and configure the model for the next project. It needs to be user extendable for custom instructions and registers. Need to be able to model actual processor IP for the different vendors. There needs to be a well-defined test process, including coverage metrics. That's a well-defined test of the model itself. We actually run, I think, something like 17,000 tests when we do code check-in on the models. Needs to be able to interface to other simulators, System Verilog, System C, the Imperas Virtual Platform Simulator. Needs to be able to interface to software debug tools. Needs to be able to interface to software analysis tools. Needs to be able to interface to architecture exploration tools. Most RISC-V instruction set simulators can meet 1 or 2, maybe at most 3 of these requirements, but that's where Imperas comes in. Our models and simulators were built to satisfy these requirements and matured through usage on non-RISC-V ISAs over the last 12, 15 years. So a little bit more detail on the RISC-V models, the fast processor models. Again, the 3 use cases. So we support the full specification, the full alphabet soup, including the privilege modes, We support the various processor IP vendors and models for developers building their own processor. The custom instructions are easily added, and the models are built using a test-driven development methodology. So we build tests at the same time we build features into the model. We use a continuous integration flow and, as I said, a large number of tests for the model and simulator. And then there is additional testing by the processor IP vendors to validate our models of their cores. So the model is extensible, as we've talked about. I won't spend a lot of time on this, but just to say, we provide the methodology, we provide templates to add new instructions, we provide code fragments for adding functionality, and there's a significant user guide and reference manual with examples to help users through this process. Custom instructions are an interesting thing in the RISC-V space. Usually when people are adding custom instructions, they're doing it to optimize a specific application or a domain. So the first thing to do when adding custom instructions is to characterize your base application without those custom instructions. So we have a methodology for doing that. And then you want to add the custom instructions and iterate. So here, just doing the basic profiling here. This is a profiling tool, and what we're showing here doing function profiling is that over 21% of execution time is in this one process line function. So now we're going to go and design the new custom instructions, add them to the application, add them to the model, and simulate again. And actually here we see that process line was reduced from 21% to 15% of the execution time. So we're trying to, with these custom instructions, remove a bottleneck in execution, improve execution this way. So here we've got custom instructions actually as a means of doing architecture analysis, architecture exploration, and optimization. So this process can be iterated, the designing of the custom instructions, doing the analysis until you get to the point where you can optimize the model itself, document the model, test the model. There are instruction coverage, line coverage tools for actually testing the model, and then generate documentation and deploy the model to your teams. So now that we've built the model, we want to use it. Going back to the design verification use case, there are three key components in the DV flow. One is the reference model up here. Second is the verification IP, and the third is that RVVI interface. There's a link there to the GitHub repository for RVVI. The thing is with RISC-V and DV that all the design choices that you make are going to impact your verification. Now, whether you add a set of extensions, whether you add specific custom instructions, that's all going to impact your DV task. And impacting the DV task means impacting schedule, resource requirements, quality, and these are all risks. So you need to have a solid DV flow. So before 2021, there was no off-the-shelf toolkit or products for DVF processors of any ISA. A year ago at the RISC-V Summit, we introduced Imperas DV, the verification IP for RISC-V. So here what we've got, Imperas reference models and the Imperas DV verification IP and the RVVI interface provides support for an asynchronous step and compare DV flow. And the asynchronous step and compare DV flow is needed to support features such as interrupts, privilege modes, debug mode, multi-heart, multi-issue and out-of-order pipelines, all these complexities at the high end of the RISC-V world. There's also the virtual platform side of this. software simulation side. So the key pieces here are the processor models, the simulator engine itself, and the tools. We've got a list of the tools here. I mentioned some of those, but also fault injection, there are OS-aware tools, timing estimation tools. And virtual platforms, software simulation, provide controllability, observability, determinism, an ease of automation, ease of delivery, ease of maintenance, provides shift left for schedule on software development, where software development is often the critical path to product delivery. And they're fast. Simulation is fast. We're running 250 to 500 million instructions per second. That means you can test many, many scenarios, which if you're doing architecture exploration, trying to optimize those custom instructions, being able to run a large number of scenarios is very important. So virtual platforms we've seen over the last 10 years or so, we've seen them be adopted more and more. They're a must-have for software system of any complexity or with quality, reliability, safety, and security environments. So I'm wrapping up here because I've been given the sign. I thought no one was following me, but anyway. So the RISC-V ISS can get you started, but a real RISC-V model plus a simulator is needed for real RISC-V projects. That's where Imperas comes in. So more information, the Imperas booth is over there. Come and find me personally. Email me. I'm sure you can track me down. Thank you very much.